Hello everyone, welcome to today's live stream. We're here with Nick. He'll be talking about inference and some things to do with probabilities. Take it away, Nick.
Yeah, probability, some relationship to quantum computation, but it's mostly about statistical inference, bias rule, maybe how to do statistical inference in very finite dimensional, very small cases. And it's like, well, maybe just a little bit intro about what the hell is the inference all about. There's like classical ways to do inference, what usually people care about, like do some inference on data in real life. Like they have some distribution from some kind of samples, they collect data, maybe it's some weather data, maybe it's some customer data, user data, and they have some model, right? It might be some probabilistic model, maybe it's some complicated neural network model. But the point is that to learn it, it may be just a statistical distribution that they're trying to learn. But the point is that we have to infer some distribution from the distribution of data. This data may be finitely sampled. Maybe we have just a few samples, or we just have some potentially infinite stream of data that we want to infer. But the point of inference is usually just given some distribution of data, a model, how to come up what distribution and how to model the distribution of the outcomes or of the data, I guess, of the whatever we observe, depending on what we want to learn. Right? There's like a few examples, and already in the Wolfram language, there's a few functions that kind of helps you with that in the classical sense, like find distribution, which is just given some random integers, find the distribution. Obviously, it's uniform, right? If you just sample from a known distribution, you can learn it and learn the parameters of that distribution. This is like a very straightforward cases of inference. There's also more advanced one when there's like the data can be even. There's some nice examples here, like images. It's like throw a bunch of images and you want to learn the distribution of those images so we can then later sample from that distributions and get a random image. in nowadays we call it like generative machine learning, whatever, generative models. Right? We learn some distribution and then we can sample from it, maybe some diffusion involved and all that, but it doesn't matter. The point is that inference involves learning something, a model or distribution. But we gonna not focus on this large examples. We're gonna just focus on very simple ones, right? Hold on, I think I collapsed too much here. Right, this is a probability intro, whatever it is. I don't need this code. Right, so we're just gonna focus on very simple examples of very finite dimensional probability vectors, like maybe unfair coins or something like three-dimensional, four-dimensional distributions. Like here, for example, I got a random probability vector, right? Three-dimensional probability vector. You can visualize it as some point on this ternary plot, right? You have a variable that can have three values. So this is the axis corresponding to each of those values. So those three numbers essentially are coordinate in this ternary plot. And it's a probability distribution, so it's normalized. It always sums up to 1, right? So this probability is there. We also can sample a conditional probability table, right? Well, you can also show it in 3D. Like last time we looked at a bunch of those simplices, right? This is a three-dimensional simplex, so you can either use the ternary list plot or you can in 3D visualize this point on this three-dimensional simplex, which is just a.
I've got a quick question about that. If you keep adding sides to a polygon, can you keep increasing the dimension on a flat space?
No, it would. I wouldn't. I think it wouldn't be unique. It's like if you.
No,
like
that would necessarily not be
unique. The scheme
unique.
is not clear. Here, it's clear how to project this three-dimensional shape into 2D, right?
Yeah, I mean, like a square would be
how would you map?
Ambiguous. Yeah, a square would be ambiguous because up down would then be x, y. That's I see what you mean. Okay.
Of course, you can come up with some clever maps in order to project the whole tetrahedron, the four-dimensional that lives in 4D into something like 3D, right? But into 2D, how do you project a tetrahedron into two-dimensional shape? You can use some kind of clever maps, but everything is going to be distorted, right?
Right. So it's a dimensionality thing of this continuous space being a certain dimensionality. If you try to take for if you try to map the tetrahedron onto a triangle or onto a square, let's say, then you're going to have dimensionality reduction. So you can't do it as like a linear map, that's for sure.
Yeah, you can use like the whole functionality of like dimension reduce function, for example. It's like has a bunch of methods. Like you can use neural networks, some UMAPs, TSNEAM, the popular ones, PCA analysis, and all that. It's just they all take care of like projecting some high dimensional data to some lower dimensional, like 2-dimensional, and you can then maybe render this, well, at least a single point you can simply project. But here we have the whole space. We want to project the whole shape that we know the dimensions of. But anyway, so yeah, so this is like I pointed this ternary product represents a single probability distribution, right? There's also a table, right? A conditional probability table, which is now 3x3 matrix, which is like some input and output representing what would happen conditionally given like if A is 1, what is the probability of B being 3, right? You can like this is completely abstract probability tables, but maybe you can imagine some model like this is like something silly I come up with. Like you can think of those 3 dimensions, maybe some humidity versus weather. It's like this conditional probability table describes what is the probability of the weather being cloudy given that it is medium humidity or something like that, right? Just some.
And this, I was gonna say like the sum total of all the elements would be 1, but that's not true, right? It's like
Yeah, you have to sum up the columns.
the
In this
columns
case, also
add to
rows
1.
work, right? In this case, it's like
What about in the 2-dimensional table? I mean, you have like 3 states for A and 3 states for B, and then probabilities for the combinations in that matrix, right?
hold on, ask what are you asking? The
A and B table. Oh, wait a
yeah,
minute.
well, they're both the same. They just
Oh,
the
I
same
see.
table.
One has the percentages.
Yeah, I've just this is a fake case. It's not some real table out there. I just took this random matrix and put some labels so that it had some meaning. Okay, it's just to make this reference to how usually conditional probability tables are learned, right? And so anyway, so the rows, the columns usually sum up to 1 because it's a conditional. This shows the input. The columns show the input to the conditional probability table. So for every case which is possible, you have to output something. So it has to sum up to 1, right? But in this case, it's a doubly stochastic matrix, as they call it, because it also works in another direction. So the rows also sum up to 1 here. So in a way, this PBA, if you sum up rows or you sum up columns, you always get all ones. So it's a bistochastic matrix or doubly stochastic. I don't know. They kind of use multiple terms. But then how you would use it, for example, in order to compute the probability of weather or our variable B, right? You just multiply it by our initial probability distribution to get the new probability vector. So that
Wait, can
given
the
some
probability that for the states of B be inferred by that matrix?
Well, that's what we are doing, all right? Given that we know the initial probability distributions for each A, right? This is our PA that we generated randomly, which is this point, right? On the simplex. Then we can just multiply this vector by this matrix, and we get a new point, new probability vector. That's going to be the probability for weather being one of those 3 cases, right? Rainy, sunny, cloudy, rainy, for example. And that's how you move in probability space, by just multiplying your conditional probability table by a probability vector. So it's just a simple dot product or inner product.
Did we know a priori PA before that table was made?
We just took a random probability distribution. We know it. We know the probability of like A being what's the probability of humidity being low, medium, high. So it's like a given. Given that we know probability for each of those 3 cases, and given this model or this conditional probability table, we can know the probability of B's. Simply by just multiplying.
Is it correct to say, given that humidity is low, the dot on that simplex will be at a specific point?
No, if you have point on the simplex represents the whole vector, right? We know that probability of humidity being low is that 8%, right?
Mhm.
It's 8%. So if
80%, then
8%
it's
is,
going to be cloudy. Sorry, so let's say if
no,
humidity
no,
is
no,
low.
low. It's 8%. So we have the probability for A,
Mhm.
right? We have probability vector for A. So
PA,
the
sorry,
first
yeah.
one, the first one is the first column. So this one is for low,
total. Mhm.
right? So we multiply this number by this whole vector, which is
Mhm.
essentially PBA 01, right? This is
Okay.
the first column. So if you multiply
Okay.
this by PA1, which is, we get a probability of 4 of those 3 cases.
Okay,
Right? That's
okay.
the
All
probability
three,
of being
okay.
sunny given and all that.
Okay, so maybe my
For it
point was
being
just if the
sunny and
probability of A was 1, so if it's 100% probability of the humidity being low, then it is the probabilities of sunny, cloudy, and rainy are exactly these probabilities on that first column.
Yeah.
Yeah.
Those are like conditional probabilities. Of course.
Conditional probabilities. Okay.
Yeah.
Okay.
It's like in order to get the final probabilities for weather being all those cases, given that we know the probability of A's, we just multiply this and get
Mhm.
the new probability vector, which sums up to 1 again, right? And that's the new point on this simplex. So we moved from here to there by multiplying A by matrix.
Mm.
So, and we can even like just to see what happens if you multiply it again and again the same vector. You kind of
Yeah.
move. You always move. You can show that you can we always move to the center.
Hold up.
It's like the center represents the noise. So it's like a uniform distribution of every case being equally likely. So if
So
you
is
reduces
PBA,
to
is that matrix the outer product of two vectors? Or
not necessarily. It's not the outer product. PBA is just some conditional probability table, just random thing, just some model that we come up with that tells you each conditional probability of A. If A is that, what would be the probability of being B, some another value, right? So that's all. That's all it has to satisfy. It just has to have some columns sum up to 1, and that's it. That's all.
wait,
All
so
the
it's not the
and
dot
it has to be
product
positive.
of some column vector and some row vector.
Well, it may be, but not. It's not.
Not
Not
a priori, right? So
It's not necessary.
you're deriving the A and B vectors from this matrix.
Yeah.
So my question earlier was actually, can you take the 3 sides of the simplex and label them with cloudy, rainy, sunny, or is that the wrong
Yeah,
way to
you
think
can
about?
label it by like yes. Well, it depends. Here we kind of mix. We represent the same space, but each point in there, it's like each point is there is has to be labeled differently, because if we started with A, which represented the humidity, and B now represents the weather, right? It's a completely different labels for the simplex. It's kind of a big, but because it's still a simplex of the same shape, we kind of can put it in the same way, in the same place. So it's a bit incorrect to just label it with something unique if we're gonna present it like this way.
Okay. So it's just a way to represent 3 probabilities.
Yeah, all
It's
probability
a space of
vectors.
3 probabilities. Yeah.
Just a way of 3-dimensional probability vectors. Right. Here's just a picture of what would happen if you just apply the same probability table to every point on the simplex, right? Instead of like picking some random point that we have with A, like how would the whole shape would collapse, right? At each iteration. So you can see that the whole shape collapses to the
So,
center.
so it's a space of all probabilities.
Yeah, so it kind of shrinks the whole space. So when if like you don't have any condition on your initial probability vector, it could have been anywhere on the simplex. As soon as you apply your probability table, the new probability vector is constrained to this first one. If you apply it again, it's going to be more constrained, and it always shrinks to the center.
So that's assuming kind of like an iterative sampling of a given state.
Yeah. If you got some model, it's not already like this simple as this humidity weather model, but it's just one that you can iterate, maybe some Markov chain or something, just going back and forth with the same matrix. Anyway, so now we go to inference. This is like the infamous Bayes rule that allows you, essentially it allows you to reverse that conditional probability table. So we now will ask the inverse question. Okay, given that the P, right, and our model, so we know the conditional probability table that we started with, right? How to infer the initial probability table, right? In linear algebra, it is simply, okay, we know that's how we get the probability of B by multiplying it. In reverse, you just multiply by inverse matrix, right? Nothing special. If you know all the numbers a priori, but the actual inverse matrix is not longer a valid stochastic matrix. So it has negative values, right? So it doesn't have the same nice interpretation as the above conditional probability table, so that you just can pick a humidity, low, medium, high, right? And given that particular column, what would be the probability of the weather being in one of those three states, right? It's no longer interpreted this way because you can't go back by doing this like forward stochastic process by just looking up the table, right? Because it now has some conditional probability table or negative entries, even though the inverse is still satisfies the same conditions as the original one, right? Everything sums up to 1. So it's in a way, that's why it's called quasi. So it's a quasi-stochastic matrix now, or doubly stochastic because both of them sum up to 1, rows and columns. But now it's no longer a valid probability process. But Bayes rule, or any inference rule for that matter, because Bayes even is not the unique one, but Bayes is the most straightforward one to introduce. It's just a way to reverse it iteratively. You can think of it as just iterating some new matrix from an arbitrary point. So we can take your original matrix, which is just our original stochastic one, right, with those 20%, 19%, and so on, and you can turn it into some different map, right, by just giving this matrix and some a priori vector. So now we have to start with some a priori knowledge about whatever we're trying to infer. So we don't know the A. Remember, we're trying to infer this point, given that this is now our observation and we know the model, and we're trying to observe this A, right? And we want to infer this A from some a priori process, and this can be just modeled by some other distribution, and it can be even be completely uninformed, which is just uniform in this case. And the point is of the bias is just if you just take this matrix, take this as your instruction of how to construct this map, multiply this matrix by vector and so on, you get a new map, right? And this new map, by multiplying by your observation, moves you somewhere in that probability space. And how it moves it, right? You can start. So A0 is your whatever your uniform distribution, your prior, completely uniform, zero knowledge prior moves. It is moved by the Bayes rule somewhere towards the A. That's kind of starts moving it. Like a single application of the Bayes rule moves it closer and closer to the target, right? So that's how the inference works. This B is it allows you to construct the map, but the map itself can move you from any point on the simplex towards the target, right?
So this is a mapping from the triangle to, I mean, I guess this is a mapping 3 space towards this direction. Is this an
Yes.
eigenvalue?
Yeah, in a way, if you think, depends what you mean. It's like a fixed point. So it's like this distribution A, I put infinity there. That's like in the limit, this Bayesian inference by applying this Bayes rule infinite amount of time would move any point from the probability space to that target, right? But even though the Bayes rule, I haven't showed you that the map that it produces is a valid stochastic map. So we can apply it by that's the point of deriving that rule. Now we turn it, our negative probabilities that we know how to interpret, right? And we turn it into some kind of procedure, which is probabilistic procedure, how to map, how to do the sample, right? Given that, do that. You first you sample from your prior, you look up this table, or you get the
Wait a
not the
minute.
prior,
Wait, these.
not the prior. Yeah.
It's interesting that this the Bayes one is the transpose of the first one. For that probability vector 1/3, 1/3.
Yes, maybe that's in that. Yes, for this one maybe. if you
Mhm.
feed it the uniform, that's the property. It's just transpose version. But the point is that you have to iterate it. For example, you apply it once, right? That gives you a new prior, right? What you do next? It's like this is our new prior. Now you take this new prior and make a new map.
Mhm.
Now it's no longer the transpose originals. It's just some
Right.
new map. Then you take this new map, you apply it to the same vector, which is our point B over here, right?
Mhm.
And you move it again. That's your like new prior again, and you and you just continue doing this process until you converge on this A. But you doing this conversion, every map is just a probabilistic stochastic map. So you're not doing anything weird with negative probabilities. So that's why it's inference. So in a way, whenever we have probability quasi-probabilistic matrices, it's like doing the inference. So that's the intuition for those negative entry probability tables. Right. So I have like a bunch of more pictures here. It's like just some random sample of points, how they move towards the target when you apply this table. You apply the bias map. I think I applied it to the wrong thing here. Yeah. So it converges to the A. All this cloud of points. By the way, the points in the corners, I think they don't. The only points that don't move. Maybe even on the edges too, because they're too deterministic. It's like picking very strict prior. It's like you're very sure, maximally sure that this is this one, and so you don't move at all. Yeah, like this is another picture
nice.
for the figures. It's like a flow showing the flow, or like this. It's like again, it's like every triangle tries to converge to the target. If you pick the maximal triangle, it's not gonna move. Right? It's fine. But anyway,
That's interesting.
now,
So there's there's like a continuous, or it looks like there's a smooth mapping that's
yeah,
kind of doing this,
totally.
and then if it's got a fixed point theorem,
Yeah, it's
or
very interesting.
a
It's like
continuous map
the
from the
bias map.
space into itself has a fixed point, at least one.
Yeah. Even though the bias rule itself is kind of discrete thing, right? You apply it once, you just move one step, right? But in a way, you can also continuously interpolate it. So it's like you can apply half of the bias rule, or even 1/3 or 1/100 of the bias rule, so that it actually makes it continuous.
So I have a slightly naive question. If you start your first prior very close to the A, to the ultimate point there, and then you apply inference, is there any way to overshoot the mark, or is there any
No.
kind of react? Yeah, it just
No, I
goes
think
from always goes
it converges.
closer. Yeah.
I think it even slows down. The closer it is to the target, it actually becomes slower. So like as you see here, it's like it makes big steps, but then it's smaller and smaller. No, it's like yeah.
But my point was, is it getting okay? So it's getting smaller because it's getting closer. It's not because of the number of iterations. That's what I'm trying to say. Like if you start very close, your first iteration is going to be small as a movement because of the closeness, not because of the number of times you've iterated.
Yes, something like that.
Okay.
Yeah. But in reality, you don't even usually do this iteratively, right? Usually because this assumes that this B that you use in order to make the step is just a known probability vector. But if you already know it, you just can, and you know the inverse of the probability conditional probability table, so you can multiply them. What's the point, right? Usually you have like a finite samples of those B, and doesn't make much sense to iterate this process. You just use it once, all the samples, because it's already not completely determining your probability, because usually it's in high dimensions. Essentially, it becomes messy. Like in this
Hmm.
case, just 3 dimensions, very simply to visualize. But in high dimensions, it's very tricky. It's in high dimensions and some with finite samples, right? That becomes tricky. But yeah, but now it's like, how do you actually simulate this process? Because that's important. It's like we want to make things computational, right? We want if you make a categorical distribution out of this probability vector, you can sample, like maybe here just 1,000 samples from that distribution that corresponds to our initial point, not the one that because our initial probability process just took from went from A to B, from B to A was our inverse inference process, right? This is shows just our distribution of A. So it's obviously it's like this is the probability vector itself. This is the histogram, or just counting it. You just show the samples, right? This is our samples. So how do you simulate it? So this essentially shows how you resample your samples given that you know the probabilities in the table, right? Given that list of samples, like maybe here are the first ones. This is just some numbers, some values 1, 2, or 3, right? And some others. So each of those samples, we just pick the corresponding column, right? As I showed you, just pick the corresponding column, which tells you the probability vector to sample from your value of B, right? That's how you simulate the forward process or any process that's just given by a nice conditional probability table like this one, right? Pick a column and then sample from this vector, and that's what it does. This is the column, probabilities, weights, and just do the random choice, and you do it for each of those samples to get the new samples. So this now represents samples from the B distribution, right? And you can show that this is a probability vector that we just computed by linear algebra by just multiplying the matrix with the vector, and this is the histogram for the samples that we produced by this just resampling method. Okay, so does this make sense? The more samples of course, the more samples you sample, the closer it would be. Here actually shows that it's not quite. You can even see the ordering of those bars are different.
Getting the probability of B, probability distribution for B, given a probability of A, and that matrix.
Yeah, and the PB, remember PB is just our PBA times PA.
Oh, right.
So that's how we go from
So what does that fixed point tell us?
A fixed point was telling our PA, we're trying to infer it backwards. It's like, okay, we don't know this probability vector, but we knew the model that we derived these samples from this because our model was probabilistic. We can imagine that this just stochastic process was acting it of this form, just taking the random choice from probabilities given by a column, right? Just a probabilistic stochastic process was acting on it. We observed some probability vectors, we observed some samples B, and then we were trying to infer probability vector A from those samples. So this is I'm showing the simple probabilistic process that goes forward, right? But the inverse is not as simple, right? You have to perform some kind of inference. So you can't simply describe it as just resampling, or you have to iterate it over and over. It's kind of weird, right? Especially when you would try to come up with interpreting quantum computation in these terms, which we're gonna go next, I guess, unless there's a more question about this particular setup. Yeah.
So this matrix keeps updating. I mean, can I see an array plot of that matrix or a matrix plot, and then see how the matrix updates given the iterations?
Well, matrix. Oh, you mean for the in this map, how the map itself updates? Well, we can try it. So, for example, let's just take this thing, this nest list. Right. I just don't actually map it. Well, we map it, but we just saw it. Just easier, like. Okay. distribute. So this is our our list of bias maps, which do array plots of those. So that's how it's updated. Well, that's how it updates. I don't know whether it's kind of doing something.
The question is, does this converge to like a?
I think so.
Yeah, it
Because
looks like it
you
converge pretty quickly.
yeah, you can show. I think it converges to what it converges. Or to something. It's not to some kind of map.
Mhm.
We can actually show that last one. Right, if you just nest. No, just show the last one over here. And just this is our converge bias. Let's see what it does. I want to kind of look similar. Maybe this kind of plot. This converge bias. So for every point, what actually want to do? It's just a single thing, right? So if we had a simplex, now let's do it differently. I just want to show 3 points. Yeah, we just want to turn a list plot of that thing. That's it. It's confused. Like you can join them. Maybe you went first. Yeah, so it kind of that's the final thing that it converges to some probabilistic map.
As
So
a
it
list
doesn't
of
tell
row
you much.
vectors plotted in this ternary plot.
Yeah,
Should it be row vectors or column vectors?
Do you
Well,
think
depends
it's
what probability you're trying to get to, right? Like that's a space of probabilities.
This map depends both on the original conditional table and on the vector, right? Because they both involved in the computation. But in the limit, it just produces the way how to go stochastically from B to A, even though the original inverse matrix was some negative probabilities, but this can stochastically produce A from B, but not, right? You can technically apply this to PB to get very close to PA, right? So basically, that's how you probabilistically get A from B, but it only would work for this particular B case. It's not like it's gonna always work for any kind of point, and that's just this probability table. It's what for every other point does something like this. But for now a particular case of B, it would transform to A. But you have to do it iteratively if you want to actually, derive it. So.
Okay. Cool.
Okay. Anyway, so we simulated the forward process. I don't have a good code that does for this simple ternary examples how to do the inverse simulation, right? I have the simulation for the quantum case, which is actually one dimension higher. So we have to go from ternary to quaternary, I guess, right? The quantum case is what actually changes. Like remember that Cubitonian that you showed last time has some kind of sphere embedded in the tetrahedron. The analog for this ternary plot is just having a sphere, and the quantum case, some unitary operation of this subqubit case is essentially you're moving your probability vectors or on this diameter, right? So it rotates your probability vector. So it's not a probability conditional probability table as we showed above, because it always shrinks your probability vectors towards the center. But if you allow by some magic transformations that move your probability vectors along a circle, some kind of maintaining the distance from the center, right? That's equivalent of quantum unitary transformations. They keep the distance from that noise vector in the middle, which corresponds to uniform distribution, keeps the distance, but it does it in higher dimensions. So that's the Cubetonian from last time, right? You can have now higher dimensional simplex where the quantum states live in this pure quantum states, live on the surface of the block sphere, and the rotations keep the probability vectors constant distance away from the center, which corresponds to the uniform distribution. But now we can apply the whole kind of intuition, probabilistic intuition of inference and forward stochastics processes in this case, right? The only difference, why is inference is important? Because it allows you to expand your probability vector back. That's the only conventional way of explaining why we can keep our probability vectors constant distance away from the center. You have to not just shrink it by applying some conditional probability tables, but also expand it back by doing this inference. So in a way, your unitary process that allow you to rotate your probability vectors have to be composed of those two operations, some forward and backward processes, which is like a forward probabilistic process and some backward retrodictive process of doing the inference.
Retrodictive.
Yeah. So
Okay.
also a nice term.
Okay, I've got a question here quickly because this kind of visually just made me think about the origin of the term quantum, like in terms of quantum mechanics and particles and stuff. And from what I understood is like the space at which electrons can be around the orbit of like an atom or something like that. And then the idea was they're in discrete like quanta of energy packets or something like that. So could it be, is there some kind of relation to what's happening here to say that the electron is not in any part of the area? There's like certain circles at which the electron is most likely to be around. And so it's kind of like a constant distance.
No, don't confuse this space with an actual physical space. This is like a probabilistic space, right? It represents a probability vectors of being in some discrete number of states. Like, for example, spin can be up or down, or it can be energy level, like some ground level, or excited level of the energy. Those are just discrete values that your system can take. And if they have some probabilities assigned to them, they form some kind of probability space of measuring maybe your system in those and measuring some outcome being in either that state or another. So that's the space which is continuous and represented by usually by a sphere, not the actual physical space of an electron moving around in 3D space. The fact that it's both 3D is just the accident. Well, obviously there's some model.
I know it visually looks the same because of the three-dimensionally, like we just chose the 3 dimensions here, but I'm just saying, like, is there some probability connection to the actual idea of like where quantum probability came from? Because there's a higher probability to find it in discrete bands or like specific distances away from like the center, as opposed to just like being anywhere in the space closer or further away from the center, or not necessarily.
I don't like, but this 3D probability space is related to spin 1/2 particles, right? So spin, at least the spin or two energy level systems somehow related to 3-dimensional space because they occupy the same. So the spin models, they do have some nice interpretations in 3D space, like those spiraling electrons moving around. So at least the spin models can be explained. That's maybe the intuition there that the 3D space somehow can be the same space. But it's usually not the way to think about it.
For sure, yeah.
Okay. So for this 4D-dimensional case, quantum, now we're gonna deal with not the 3D probability vectors, but 4D. The only case, in a way, it's much simpler because the only quasi-conditional probability table that you have to inverse in quantum case is this one. It's like you can there are multiple choices, but if you pick your basis right, you need to only explain the action of this particular matrix, right? Which is again contains some negative entries. So in a way, we have to invert it by applying some sort of inference, right? Because that's the only matrix that keeps your quantum states at constant distance from the center, right? In this circuit, like this is a simple circuit, which is that we're gonna try to simulate, which is like given some state. That's why it contains too much information. Don't need. Let me. Actually, it's fine. Well, we can remove this and put this on the top. It's like for the state you have any quantum state, a qubit, you have a 4-dimensional probability vector, right? And for every gate, which can be thought of probability as a quantum state with 2 outgoing wires, can also be thought of as a probability vectors, right? But because they collide there, it's like this is like the interaction between something sampled from the state and something sampled from this left side of the gate. That's where the interaction happens of those things, because they go kind of in the opposite direction. That's where this matrix models this interface between them. Essentially, this is like represents the identity. What I do here is just simply take the identity quantum operator, which is just the identity matrix, and turn it into a nice basis. This nice probabilistic basis. It tells you how to convert Qs to the inverse Qs or red ones to the cyan ones. This is like just churning the basis. In a way, you can think of like the particles, or if you actually think of the particles that have, or well, okay, let's think of them as particles. It's like the quantum states emits some of the particles that can be one of the 4 states, right? And the quantum gate emits pairs of particles that can be in one of each can be in one of the 4 states, or in total 16, right? So that's why there's 16 bars in there, because it emits pairs of
Wait,
particles.
so why is a gate emitting particles? I thought a gate just observes a
Well,
particular.
well, you kind of think of it, because in reality, how do you actually physically construct the gate? It's some kind of photon hits the qubit with a laser, or it's a magnetic field turns on. There's some kind of interaction with the qubit, and the interaction is made of some kind of field. Therefore, there are some particles, usually photons, that interact with whatever your qubit is made of. So you can think of this some source of something, right? But this source, and as a probabilistic source, it can be thought even of as a probabilistic source of those pairs, right? The only difference is that it goes kind of in opposite direction. Even like you can even think of it as going backwards in time.
Okay, hold on. There's a whole lot of stuff going on there that
Yes.
I don't 100% understand. So, okay, I thought a gate was like the moment at which you actually collapse probabilities to get like a more definite state of, like, maybe they say the spin or the.
You don't think about collapsing for now. It can be explained in the same way, but collapse is usually associated to the measurement.
Okay, so let's talk about, like, I thought it was like, let's say for example, a polarizing thing. So the gate is kind of like, okay, if you polarize it vertically, then you know for sure whatever comes out the other end is not going to be
yeah, it's gonna block the horizontally.
Yeah, it's not gonna have like a horizontal angle to it. So you kind of like logically control certain traits of the quantum state of the quantum circuit as it flows through each gate, and then that's how you get the result. Maybe you can just define what a gate actually does in a quantum circuit. Like, are you like, when you create a quantum computer, you add all these gates. So are the gates the same as like the logic gates, or is that a different concept? Am I confusing the two things now?
Well, we just introduced like a probabilistic view of how probability vectors are manipulated. Here is essentially the same thing. When I talk about quantum operator, well, I already have U, I think, right? When you talk about this quantum operator U, it's just some matrix. Again, right? The only problem is that conventionally it's represented by a matrix of with complex amplitudes, right? So it's a matrix, and you multiply it by some vector to get a new vector. So you do essentially the same thing we did with probabilities, but conventionally you do it with the complex numbers. But there is some straightforward basis conversion that you can always, by increasing the dimension, you can just get rid of complex numbers and think of the both quantum states and gates as just probability vectors or probability tables.
Sure,
But
sure,
you
sure.
still
Okay.
multiply them together in order to get from one probability vector to another. In the classical probability case, when you do your stochastic process, you multiply a matrix conditional probability table by probability vector to get a new one, or you do a sampling. Here it's essentially the same thing. You just the U1, right? When you convert, let me leave this table here. When you do the conventional representations of the quantum gate and turn it into some nice basis, now it turns into some quasi-conditional probability table. That's the point, right? By picking a nice basis, the table becomes quasi-probabilistic.
Okay.
Right? But we know how to deal with those now, because as soon as we see negative probabilities, we just think of them. Okay, this can be decomposed into this forward and backwards process. Some does the forward probabilistic process by shrinking your probability space, another doing the inference by expanding it, so that you keep the distance, right? Because when you apply this quasi-stochastic matrix to the vector, it always keeps the same distance away from the center. If it was before.
So
Your
is it fair?
Yeah.
So is it
Yep.
fair to say that when the qubit passes through the gate, it still maintains its quantum state? It just, you get a what are you gaining from the gate? Like what are you getting from it? Like a more accurate spin? Like are you kind of just polarizing out some probabilities of
you're not gaining
some
anything.
aspects?
So here you started from this arrow, you just applied the gate, you rotated it.
You rotated it, yes, yeah, but along a specific axis, and that axis.
Well, it doesn't matter which specific axis. You essentially for the qubits, for a single qubit, just represent some rotation, because it keeps the state pure, right? It just rotates this vector, probability vector, because even though it's a quantum state, in this picture it could also be thought of as a probability vector because it's inside of the simplex, right? So you're just rotating the probability vector.
But my point is, like, the gate, when you practically do it, is it always going to rotate whatever qubit that goes through it along a specific plane, or can it rotate it in any way?
Like well, yeah, it does some weird rotation. Usually on the qubit, it like, yes, it's essentially the same as doing if you know about earlier angles, right? It's like yeah, this is a good documentation. It's like,
can we zoom in on a little bit on that? It's a little bit small.
It's like it's a way to parameterize rotations in 3D space, right? Because if unitary gate is a 3D rotation, you can parameterize it by 3 angles. A different way of doing it, but you can make a correspondence between a unitary gate acting on a single qubit to 3 angles, right? It also, maybe some pilots know it like roll, pitch, yaw angles. It's like the same either roll, pitch, or yaw. Yeah, it's like you can either convert to this 3 angles or
yes, sure, okay,
angles. So yeah. So some unitary gates is the same as giving you these 3 angles.
A unitary gate, okay.
Well, the most basic computational component you can have in quantum circuits. Right.
Okay, but I mean, then that's going to move it in any direction along the surface of that block sphere. If it
well, it's going to rotate. Not like, yeah, it's like this rotation maybe doesn't count because it's still just on a vector, it doesn't represent anything, right? But if you, because you also mod out the phase, but if you think of the flag, then this rotation also changes the phase of the quantum state, even though the phase itself is not observable.
Okay. Just a quick
Okay.
side question. What are those little blotches on your block sphere here?
Well, because
the
I just
sphere being rendered
because I
twice.
just put one sphere on top of another without thinking.
Okay.
Yeah.
It looks kind of cool, actually.
I mean, is the second sphere being rotated relative to the first one?
Well, they're on the same graphics. Yeah.
Okay.
They just overlap each other, so it kind of confuses the rendering engine.
Mm-hmm.
It's like hexagon. It's kind of crazy. Yeah. Okay.
Right. So, okay. So the gate here is just rotating the probability vector, right? If you choose
Okay,
the different bases, you can, because it's like this is like in the original basis, the red points, those 4 red points. You can think of those 4 different discrete values that your qubit can take. If you instead choose for the output of the gate the inverse of those or conjugate of those, the cyan points, you can turn your unitary gate into just a probability vector. So now it becomes a nice conditional probability table, right? Which is like a joint one. That's what is shown over here. So if you just it's essentially if you inverse this arrow here, right? It's like this goes in this direction. There's a particle going in this direction. But by default, it's a different. The gate assumes that you have an input, right? By default, it's this. You're like reading your computation from left to right. So that's why in this direction, your unitary gate and every kind of gate or quantum process has some negative probabilities assigned to it. But as soon as you inverse the input for your gate, now it becomes just a state with 2 outputs. So now you can think of it as a probability distribution, but for the pairs, right? And you can do it for more complicated gates with more wires coming in and coming out. You can turn it into a probability vector, but now you have to think of the direction, right? So now if your state is sampling this raw state, the sample goes in this direction, there's some kind of collision happening, and that collision have to be resolved. And this resolution is just can be done by this, essentially this identity. An identity by itself is just like one matrix, identity matrix. It doesn't do anything. But as soon as you convert it into this double basis, one is in forward direction, other in the backward direction, it becomes this. It becomes this diagonal one instead with negative entries. So that's essentially you can convert every process in the quantum circuit into this process where every gate, every channel, even every measurement can be turned into a probability distribution. But then you just put this single matrix on the wires like that. So you kind of reduce your problem of negativity and negative probability to only happening in the wires, right? So and that's the only thing that we have to simulate. So it's in a way, it's much simpler. We know how to simulate forward processes by resampling, and the inference is more complicated to simulate, but this at least we only know we have to simulate the only single case, right? So, and for this particular matrix, I have a simulation, so bear with me. Maybe we read a little bit of code. This is like simulates this process. Okay, this simple loop. So we want to follow, where's the dynamic? Yeah, put this here, right? We want to, we can initialize, this is the actual true distribution that we want, right? That's what happens when you just apply U gate to the state, right? That's distribution you want to get. But we want to simulate this process of actually sampling. This is like collecting statistics of the output of that gate. And this is the loop I wrote that simulates it in a simple way, in a straightforward way. Remember that we're trying to simulate this matrix, right? So let's see. Let's see what is actually doing. So it's just some kind of infinite process. You sample from U, right? This is just taking the random choice from U. This is this distribution. Sample random choice from P. This is sampling from this distribution, right? And then we just check. Okay, look at this matrix. The only thing that changes is whether they're the same or equal or not equal. right? It's like this is the one is where the Q2 is not equal to Q2 inverse, right? And so on. So when they are not equal is a very simple case, which is all the ones in that probability table, quasi-probability table. So we just ignore it and we just increment our counter. We are trying to collect the statistics on the right, right? We just increment the corresponding counter on the right. But if they're equal, we just decrement it. So it's like by 2, right? So that's just simulating how would you straightforwardly collect statistics, but you also have to perform some post selection, because we're not just collecting it straightforwardly by incrementing it, but we're also subtracting it. So, right? So it's not a nice physically simulatable process, because usually you don't do this kind of destructive thing on the distribution that you're sampling, because again, imagine that it's an actual quantum experiment, right? And for a second, pretend that this is the measurement, which is here it's not, but you can think of it this way too, right?
Yeah.
What actually happens in a single run of the experiment, right? You just fire the electron or the photon, right? Do some rotation on it and measure it. You just observe a single instance of whatever this resulting electron, the state of that resulting electron, right? You just you just sample a single thing, right? But this simulation tells you that somehow if the outer loop represents the statistics that you collect, you have to somehow discard some of the samples that you've already collected. And that's obviously not what's happening in the quantum experiments. You can just drop the cases in our collection. It's like some of the universe that do not exist, right? It's like you discarding the universes out that you already sampled.
Is that kind of like how some of these experiments seem to have retrocausality, because you have to like
exactly.
Yeah.
It's like there's some kind of that's exactly the source of this weird things. You have to discard some of the universe, or destructively interfere some of them.
You must forget the evidence of your eyes and ears and pretend that
Yeah.
what you've witnessed does not exist.
Yeah.
Wait, so that's what the negative probabilities refer to? It's sort of.
Yeah, this is refers to this retrocausality thing, or some kind of destructive interference. You have to discard some of the cases. So if you want some physical interpretation, it's not very straightforward. It doesn't become very, because you only see every sample once. You don't discard anything. You just collect the statistics, right? You don't observe something that is being destroyed. So this straightforward simulation, even though it's like directly.
So is it like taking like a certain distribution and subtracting out some other one?
No, subtracting some value. It's like
Yeah.
if I actually run it, I haven't run it. You can see this. See, it collects. It's like goes back and it's like up and down. It's like, and it converges to the actual distribution. So that sometimes it breaks when it retorted. Okay, good now. So so this simulation is not very physical. That's what the only thing I'm getting at. Right? It's not really physical, but because we just directly tried to model this process. But I have something.
It's not physical in what sense? Because obviously it physically does actually happen in reality. But what aspects is
well, if you interpret it like with some weird ways, you can come up with. But I want something like very computational and constructive, right? If we, it's like if you imagine like some sort of multi-way system. Okay, stochastic processes, probabilistic processes, okay. It's like it's just some kind of multiple rules act on the state, and what we can branch. But this kind of thing essentially corresponds to some destructive interference of those branches.
Isn't it just a convergence of the multi-way paths?
No, they're not convergent. It's like saying, okay, in this branch we get this result where they collided. You have to you have to discard some other branches. It's like branch action. So it's like
spooky action at a distant branch.
yeah, it's like, so we can't really think of each of the branches, their independent universe. They somehow have to interfere with each other and destructively.
That's crazy. So you almost need like a quantum branchial space. overlaid on top of your
Yeah.
multi-way system.
Essentially, it becomes very weird if you start thinking of those as an actual branches that we occupy, right? Because in order to explain all the statistics, you have to somehow explain this destructive interference of branches. So
Crazy.
it's very
Okay.
weird. But
It's starting to make sense now,
but I
though.
think,
Mm.
yeah, but I think I have some resolution to it, right?
Hey, great.
Right, that's all right. So the simulation for this same matrix, which I called backtracking with inhibition. So so essentially we're gonna try to simulate the same thing, but what we do, right? We introduce some inhibitors. So inhibitors, instead of destructively interfere things, we introduce some sort of things that prevent in the quantum gate, right? There's some, think of them, there's some kind of form, there's some amount of inhibitors contained in the gate that prevent the sample going to the right for some amount of operations, right? So that it has to allow to retry. That's why I said backtracking. It's essentially you have to retry the state. In the inference case, you can also think of it. In order to perform the inference, we have to sample many times, right? But as soon as when you see a single sample, there's no way to perform the inference, right? In order to perform the inference, you have to fill the distribution from the state, not just a single sample, right? Because otherwise it won't be able to reproduce the statistics. You have to actually know the distribution, not just a single sample, right? So in order to produce this effect of making an inference, you have to fill out the distribution, so you have to resample it. But in order to resample it, of course, we don't observe that there's some multiple electrons coming out in every experimental run, right? We only see a single experiment, a single electron. So we can imagine that in order to fill out the distribution of the quantum state, you have to retry everything that happened before that gate in order to fill out the distribution. So I'm thinking of it as in the terms of some reverse rule acting on that electron, right? It's like going back in time. So just in order to retry this whole process again, you have to send this electron back to its origin so that it's got resampled. Maybe it's going back way back, maybe even to the Big Bang, but it's like depending on how many interactions it was undergoing. Maybe it's a new electron. It was just created from space itself or whatever.
Okay.
So all the way to its origin so that it got resampled so that you now get a new sample, right? The quantum gate fills this new sample. I get checks all these conditions for this table, right? And it either allows it to pass through or not, right? But those inhibitors does not allow it to go through easily, right? That's why I called it inhibitors. It's inhibiting the free pass of the electron through the gate. And there's always every quantum process can be initialized. You can think of it as all of those quantum processes are initialized with some amount of inhibitors a priori, right? And when it just fills out the electron, the amount of inhibitors diminish, so you decrease. So until there's like no inhibitors left, or there are two very small amount of them left, so that it can't inhibit that particular electron in that state, only then this electron passes through, and that's what we observe. So in a way, it's a very weird situation, but at least it's a computational one. You can think
So
of
you're
it as
trying to
just
make like
trying
Bayesian
backwards and
inference.
reverse. Well, effectively, that's what it is, right? But now this inference is embedded in this computational process with a nice interpretation that we only see a single outcome every experimental run, right? It's like in the inference happening underneath of that quantum experiment just by the by the nature of that retrying this process all over again until it reaches some equilibrium of sorts, and then it passes through.
But you would have to change the inhibitors over time to make some
Yeah,
kind of.
you're changing it. The inhibitors do not reverse in time, so it's not like complete time reversal. It's like you initiate it.
Yeah.
Yeah, it's like imagine you initialized your number of inhibitors with some large amount of them, right? Your electron, the first try of the electron is going through that state. It sees it. The inhibitor maybe discards one of them, just removes one of the inhibitors, goes back to its origin, retries it again, comes back, and it just goes back and forth until all the inhibitors diminish. As a process, you essentially infer the distribution in the form of the distribution of those leftover inhibitors.
Yeah, that
So
makes sense. But
you can
how are
mimic.
how are you retrying the electron? If the electron
So
only
you
goes
retry it. It's like I'm saying that it's like retrying it by going backwards in time, but in computational terms, it just means you apply the reverse rule of that, right? Imagine that it's like, okay, physical laws are reversible
yeah.
to some degree, right? At least there is a CPT theory. CPT symmetry is still the fundamental symmetry. You can reverse time together with charge conjugation and parity and all that, right?
Okay.
Until under this symmetry, which is fundamental, you can imagine that in order to inverse time, you send back the positron or whatever by applying the reverse rule locally. It's like it propagates this whole reversal across the time, across space too, right? Because it's has to interact with everything that it's interacted with in the past. So that you, but in the way computation is still moving forward, you just apply the reverse rule. So it's like you still, like in the physics project terminology, you're still building up the causal graph of your computations, which is just building the space-time of interactions moving forward, right? It still so in a way that still makes the classical space-time. So it's a classical space-time model, but some of the events are effectively reverse rules, reverse events.
You
Because
say that the interactions make a space-time in a classical way. Are you talking about the causal relationships?
Yeah. Each interaction event, updating event, is just some space-time event is just some node in the causal graph, and they causally connected to each other. But those updating events can be either forward or backwards, right? You can perform this dichotomy of rules first. It's like if you, for example, in NKS, let me find this page of Steven about reversible rules. He has this nice model about reversible CAs. Very good. There's like some second order CA that you have to go look up
While you
2 steps
while
backward.
while you're bringing that up, we had some questions here. So Thomas Murph, is there a sense of monotonicity in the convergence that would invoke fixed point theorems? And then was specifically
Yes.
thinking of fixed point iteration with Kleen's fixed point theorem.
I don't know what this theorem is all about, but there is a fixed point like we showed in the Bayesian rule application, right? Because we effectively perform an inference, right? There's a fixed point, so we always converge to some final distribution then. Is that in that quantum inhibitor case, we just converge into some final distribution of inhibitors. So if you start with many inhibitors, like in the uniform state, we could have had like maybe, because it's a 4-dimensional, we can have thousands of those, thousand of those, 1,000 of those. We can start with this 4,000 inhibitors in the quantum gate, which is completely random. It doesn't represent any distribution. But when this interaction happens of electron retrying and interacting with those inhibitors until they still, because initially they're all still there, because it's like their distribution is completely uniform and random, but there are finite amount of them, so each interaction diminishes, right? And in the end, it's kind of takes some form of the final distribution that you want to take. So that at the end, this infers some distribution, and the electron that actually manages to pass through the gate, because there's no inhibitors left, follows the correct statistical distribution that we actually observe. All right.
I mean, it's a cool idea. I'm just trying to visualize how would this physically work. Was this purely hypothetical, assuming there's some way to push the electron back in time? Like, I don't understand how you would construct such a thing. Or is this just purely based on like the mathematics allows you to do such a thing?
I'm still looking for that page with, oh yeah, I found it. All right. I was looking for this page about reversible CA. You see, there's like, given a CA, right? You can
Mhm.
always make a one that looks an additional step back, right? You look at the 2 steps back, and you can just think of them like this one over there. It's like white here, black there. This is you can think of this as a forward rule, this
Mhm.
as a backward rule, right?
Mhm.
Backwards rule are the ones that have black cell 2 steps back, and forward rules are the cells that have white cell 2 steps back, right? So as soon as you have this dichotomy of rules, that you can think of one of them moving forward, another one moving backwards, right? And you have some nice distribution that you always have more forward rules acting at like across state than backwards rules, so that you always move time forwards, right? That's what the condition for probability distribution summing up to 1 essentially is. Because you're summing up to 1, you have more positive things than negative, even though you have in the distribution itself some negative things and some positive things. The fact that you sum up to the positive number means that you have an excess of positive over the negative ones. So you have more forward rules, more forward moving rules than backward moving rules, right? And if you have that state of the excess of forward rules, if you apply it and you effectively can have a system that maintains this distribution of forward of this excess, that you always have one, right? Then you can think of it as this quantumly, because now this corresponds to the same case that I showed you, that we just maintaining the distribution. We just sometimes locally can think of it some backwards rule acting on it, and this retries the state back because it's a backward state, right? It kind of goes locally backwards in time, retries the probability distribution. Maybe there's a multi-way system too, and just go back and forth until all the inhibitors are running out. But it's still computation because you can have backwards and forward rules, even though computation moving back. So it's like computational time is only moving forward, even though effectively as an observer embedded in the system, you can be acted on with forward and backwards rule, right? You can reverse time. Your physical laws can go backwards because there's some time symmetry. It's no problem with that, right? So it tries it, and those inhibitors tries to continue to run out until it's actually the inference is complete, and then that's going forward. So that's essentially, and it's always going to move forward because there's the excess of forward rules globally. Even though it can be performed actual retries, its number of retries can be exponentially large, even though, but in the limit it still holds, right? And that's how it, and that's the interpretation for this thing. And this is the actual loop that with those inhibitors. Here it's
Okay.
here it shows like the true distribution. Here it shows. Let me reset it. Let me reset the A counts. Right. This is some error. We are again starting with some finite distribution with zero, and we collecting it. Like this, the outer loop is the statistics we collect with every time. Every body here is just one experimental run, and here it's just the inhibition thing happening. See this, like every time it checks whether this particular sample is inhibited or not, and it removes one inhibitor. Yeah, and if there's not inhibited, this loop breaks, and then it goes again. Right, this is where the statistics increases. Then we actually success is achieved. Our experimental run is complete, and now because we assume that it's a next experimental run, we again reset all the inhibitors back to the uniform, this 4 million number of inhibitors again, right? And we repeat. So that's what statistically what actually happens.
Okay.
All the inhibitors has to diminish in order just to observe all the samples. A single sample is just only happens when all the inhibitors are inhibited enough so that you can pass through all of this and increment it. Because
Okay.
yeah, this loop has
Is
to finish. Essentially, this is all the represents all the retries.
yeah.
Yeah.
So is there feels like some kind of at least aesthetically a connection between inhibitors and like entropy somehow. Like
Well, entropy in these pictures, in these representations, you have entropy We have multiple types of entropys. First of all, for the conventional quantum case, we have one Neumann entropy, which is essentially represents the distance in the Bloch sphere from the center. So like the pure states that are on the surface, they have entropy zero entropy, right?
Okay.
Or one bit of information, if you wish.
Okay.
The uniformly mixed state at the center have one entropy, one bit of entropy, so it's maximum for the qubit.
Okay.
So that's what entropy, the quantum entropy is. But you also can compute the Shannon entropy because you have the probability vectors.
Mm.
It's a little different. This is actually not have different values on the surface. So even though you're rotating the pure state, if the von Neumann entropy keeps zero, stays zero,
Mm-hmm.
right? The actual Shannon entropy of the probability vector is actually varies a little bit. So they have, so it's not constant. So it's kind of, but it's still somewhat fixed distance from the center still, but not constant. You can show it.
So is there maybe an analogy there in that as you reduce the inhibitors, you're reducing the entropy?
Well, you actually, yes, for the inhibitors, if you have because when you start for this uniform distribution of inhibitors, that's the maximum entropy, right? That's a completely noise. As soon as you reduce it and do something extra with it, like in this loop, we still have to implement the action of this matrix. Somehow we increase the inhibitor.
Yeah.
Even sometimes you have to actually increase the inhibitor. You have to drop it, right? But as an effect, this is like this distribution becomes less uniform. So that means you reduce its entropy.
It's almost like if you thought of it as information, this is almost like a noise gate or something, where as you reduce the noise, information can pass through, or like a signal can pass through the noise that you can then pick up on. And then you can measure the information or the distribution of the information somehow by how you're adjusting the noise, or like at what frequencies you reduce the noise. It's like picking up an audio signal based on allowing certain channels to actually pass through without actually measuring the noise, without actually measuring the audio signal directly. You just infer it based on what you do to the noise. I don't know.
Maybe there's a nice informational theoretical explanation what actually happens to entropy and information in this case. We can think it through. It's like I haven't thought of it yet. So the inhibitors, okay, they have inhibitors that reduce the entropy, right?
Mm-hmm.
Which means that we have to somehow increase it, right? And the quantum state, the von Neumann entropy, as I already said, doesn't change anything, right? It's not changed, so it's a state.
Yeah, that stays the same.
The same one stays the same.
Mm.
So in a way, the background always acts as a constant rate, as a constant source of information. In a way, in this case, so the background 0 point field probably, or it's a space-time itself. It's acting as the source of this that can reduce the entropy. But effectively, it's reduced by the nature of this retries, right? It's like observationally.
But it depends on the observer, because it could be that space-time is reducing the entropy to the universe as an observer, but you're inside you're an observer that's trying to extract information from messages passed by another observer, not just the universe as a whole. So from that perspective, the universe could be increasing entropy, and you're trying to take the inverse of that to understand information that's been transmitted from another system inside the environment. This is where information gets like crazy, because it's like, whose information you're talking about, like a pure random packet of information that's totally entropic has maximal information from like in a different perspective, because there's no compression you can do to it. There's no reducible, it's irreducible. So it has maximal information, but it's useless to you as an observer. Pure randomness, you can't do anything with it.
Okay, stop. I think I lost the connection for a sec there.
Oh,
Can you-
oh, whoops. Okay.
Lost information.
The noise entropy of the
Our channel
internet.
is not. Yeah,
Yeah. Oh
some
god.
information leaked there. Leakage. What were you saying?
Yeah. Okay. So this is maybe a tangent, but what I was saying was, it seems like when you try to define information, it depends on whose perspective you're trying to determine the information. So in other words, a packet of information that is purely random, it's maximal entropic, cannot be reduced in any way whatsoever. There's no compressed representation of that random noise envelope, a letter of like random numbers and letters that you received in the mail. So, but it's useless to you as an observer. There's nothing you can do with that. So you could say there's no information in it. The type of information that's relevant to you is like a letter that's written by your friend with like information on it that's relevant to you as the observer. So high entropy could represent high information content, but it depends on who the observer is. If you're the observer trying to do something with that information, it's low there's no useful information.
In the classical inference, it's also related to the prior, your original prior, when we done classic Bayesian inference. Your prior,
that's
when
a
you
good
started
point.
from the highest entropic state, it just represents your minimum knowledge, right? You don't assume anything. You don't assume any knowledge about the actual probability state A, right? You just assume nothing about it, and then you start moving it by reducing the entropy and increasing the information, right? So the whole process of inference increases the information by the nature of what I don't know where it's like actually coming from, because it's not a thermodynamical system we're just thinking about, right?
Yeah.
So
I'm trying to cross.
Inhibitor state is just our prior. It's just like acts as an indirect prior for our distribution.
Okay, that makes sense. Yeah, I think I'm trying to cross too many different analogies there at the same time. I'm trying to think of it like in society, in information theory, and quantum mechanics at the same time. It's kind of difficult to make the simplex of all three of those dimensions at the same time. But yeah, just purely information theoretic, there's a cool analogy to information entropy there.
Yeah.
Okay, cool. So what are you gonna call this device?
I have this. I don't know. Do you have any suggestions?
A quantum governor or something.
Governor, because it's what inhibits everything.
Yeah. Well, it's like a governor in a car. It like limits the speed of which you can travel.
The kid buys a go-kart. The first thing you want to do is take that thing out.
Take the governor.
So is this converging to something? It is. It is.
No, it's in a way it stops converging any further because it depends only on the number of initial inhibitors. It's like the more initial inhibitors you have, the more correct it would be, but it also would take more time because you have more inhibitors to reduce to diminish. So it's gonna converge slower, but to a more precise state. So there's some kind of balance going on in the simulation. This is even kind of can suggest some actual quantum experiments. By assuming that there's some finite number of them, what is the maximum precision you can extract from the measuring quantum states? Because this kind of purely statistical precision doesn't refer to any interaction with the environment and decoherence effects. It's like purely from the fact that there's some finite amount of things modeling this stuff. There's a finite amount of sampled from here, sampled from the distribution. There's maybe finite amount of stuff in the quantum gate, right? Everything can be quantum, so everything can be finite, and they can all diminish. So there's always some limit to all of those distributions. So it's like a purely statistical source of error in every quantum experiment that we have, and maybe we can measure it somehow. But you have, but you have to precisely measure it. But we already have a lot of problem with noise and decoherence, so already.
Yeah, the only part I disagree with you on is when you say the observers can go back in time, and there's no problem with that. Every movie I've seen where you go back in time and then you come back, there's always some kind of problem. There's some kind of
Oh,
plot
that's
twist
that's
where
not this kind
that's
of
not a good.
backwards. It's not this kind of moving backwards scenario. You're not just jumping around, right, to the state exactly the same, but with you in it, right? That's much more complicated. You just gradually turn on the knob in the backwards direction. You're just reversing yourself locally, right, and reversing everything around you with whatever you interacted with.
But as you reverse time, you're actually reversing the turning of the knob, so you never go anywhere because you're turning the knob backwards. Like if you have a, if you have a switch that can make you go backwards in time, as you try to like go backwards in time, it's you just turning the knob off again. So
well, that's why observers can't do it, but the actual nature can, then because those inhibitors are there.
You see the inhibitors again. I knew it. So there's some like universal quantum governor that inhibits us from going back in time.
Yeah, too much.
Well, I mean,
it makes it increasingly difficult doing so.
If you're driving a car and there's a wall there, or an obstacle, right? Then before you hit the obstacle, you swerve to avoid it. So it's almost like before the collision happened, something retrocausality you to swerve.
You could take
So
that
I
analogy
mean,
to
the
say,
collision didn't happen because before that would have happened, you swerved to avoid it because you have a predictive mechanism in your mind to do this avoidance thing.
Predictive mechanism is not predictive mechanism. Predictive mechanism is straightforward. It's just this doing this forward moving computation of just resampling stuff.
You could think of it as maybe a mini world scenario where there's certain versions of you that didn't swerve out of the way of hitting the wall. And then you could say, okay, those of you who did swerve out of the way and hit the wall and missed hitting the wall are the versions of you that are able to notice that the wall was there or something. I don't know. I'm trying to, there's some,
I don't know, for waves, it's like you have this wave front coming, and then there's this obstacle, and some of the a wave is never like just by itself. It's like one of these nodes, right, or undulations that has like precursor like little waves that like are going before it, and so if those start like bouncing back, then you have like a bunch of wave collisions that are propagating backwards. But that's all forward in times in this scenario.
Yeah.
I don't know how to deal with this ontology of backwards in time or retrocausation or.
Well, it's not necessarily
an
quantum
inhibitor.
that waves analogy. It's almost like you can draw after. It's almost like after the wave has. Yeah. It's like there's certain, so if you were to take it as like the electron or the the double slit experiment kind of scenario, it's almost as if it's a wave up until a point where there is some information leakage into the environment, and then it's not a wave up until that point, but then the wave continues again until the next point, which you can take a sampling or a measurement or an observation. So it's kind of like what you're saying, where there's this maybe a pilot wave, but at the point the pilot wave actually hits something, it like collapses into a straight line again, and then the wave propagates again from that point forward. That's the way I visualize it. It's not like a continuous wave over the entire space, because then it's just it's not like a quantum. It doesn't have that spooky quantum effect anymore.
Well, the spooky quantum effect and all the non-local effects that quantum computation have and quantum theory have is just can be explained again here similarly to just having this retries, right? Every retry, because you're retrying the same situation, you're going back to its origin. That's all. That's the source of all of this non-locality.
That kind of makes sense. So if you think of it back to the double slit experiment, it's like retrying to get through the gaps, and then only at the points where it actually gets through the gaps is where the electron exists.
In the measurement device that measures the actual dot on the screen, there are some inhibitors that send the electron backwards to the slits so that it can retry to go either from one to another.
Yeah.
Right.
So it looks like it collapsed to be in specifically that point or whatever, but it's actually just retried a million times since the dawn of time to line up perfectly to get through that, to get to that exact spot.
Okay.
Well, it's always interesting to keep in mind that the single slit experiment also has a waveform probability distribution on the far end.
It just doesn't have the interference pattern, right?
It just doesn't have an interference, right?
Well, it just means your distribution of the position is very high dimensional. Here we're just dealing with qubits. It's not very high dimensional. But if you discretize your position, you'll make a higher dimensional one. And now you have many more states for your electron to be in. But there's still inhibitors that inhibiting all of them. Right? You can still make the same kind of discretized version of it. So it's like mathematically everything is equivalent. It's just a matter of interpretation and making it computational. But I think that kind of makes it computational. That's why I like this approach.
Yeah, it's computational. That's actually a nice way of framing it. Yeah. Because all the other ways you kind of like you're dealing with maybe continuous mathematics, is that one way to describe it? Whereas this is like maybe like a type of discrete approach, something like that.
Right.
Computational approach, not
What's a computational? I think even the continuous case can be increased in a similar fashion. You just have to go from discrete distributions to continuous ones. But we can do this inhibition even in the continuous. You can come up with a continuous interpretation of inhibitors too. Pretty sure.
Okay. Yeah, I'm sure it's possible. I just would have to think what that looks like. This is cool, but it's going down now. So it's went from 7.1 in the first one. Now it went down to 6 now.
It's gonna be converging slowly. It's like if I increase the number of inhibitors, it's gonna then the conversion is gonna be slower, but to a better precision. So it's kind of the balance between those. It's like if I turn it up to 1000 inhibitors, it's like look how slow each retry is happening. Right?
Wow.
But it's gonna ultimately converge to a better number because it has to diminish all of those 1000 things first in order to get one sample.
Interesting. Okay, cool. Is that we're just gonna let it run? How long would it have to run for? Like infinity years or something less than that?
Depends what accuracy you want. You can stop right there. It's like it's already pretty close to whatever can be reproduced in actual quantum computers nowadays. So that's why it's very hard to test. It's like if you don't even if you don't even apply quantum gate, you just initialize your qubit to a 0 state and measure it, you already have an error there. It's like sometimes even it's 0, you can still measure it with 95% 1, something like that, right? So it's not perfect, but yeah.
All right, cool. Yeah, thanks for running through that with us. It seems like there's some interesting connections here that I didn't initially realize was quite cool with regards to probability theory, Bayesian inference, and quantum mechanics. And there's a very natural connection to all of these, which I never really appreciated, because normally when you study like quantum mechanics, it's always like in the context of physics, and like maybe then you talk about like tabletop experiments or cosmology or that kind of thing. But thinking of it in terms of just probability theory and statistics and stuff. This is pretty cool.
Yeah.
I wonder if there's any ideas from quantum mechanics that informs statistics.
No, in some crazy alternative science, alternative histories of science, you can imagine that maybe this kind of approach to probability theory or more interpretation of negative probabilities could have come up before quantum theory, and with Hilbert space were invented. If it was before, maybe we wouldn't have a Hilbert space.
Yeah.
Yeah, I still don't know what to make about negative probabilities in any sort of classical way, except there might be a probability of there having a deficit accumulate.
Yeah,
in some
there's
quantity.
some inhibition and promotion. There's like this kind of happens in biological systems, right? This as soon as you have some system that has these inhibitions and promotions happening, with some catalysis involved, then you can express them using quasi probabilities in essentially the same way. So if it happens in biological system, you can even call a biological system with inhibitors and promoters as some quantum system, but on a larger scale, because mathematically it's equivalent.
Yeah, that
In some
sounds
sense.
like a topic for a future live stream. I would really want to investigate that. Oh, can we do like quantum biology? Something about like photosynthesis and proton interactions of mitochondria or something in terms of like how the quantum weirdness works at a biological level. I don't know if you've looked at much at that before.
Not really.
So
It
that's
would be really fun to explore it. Yes.
Okay, we need to go, but yeah, here's the notebook. Also, I'd like to announce that what's the announcement? Oh, soon we will have finished planning for winter school. So Wolfram Winter School is going to be happening in the second week of next year. It's going to be 2 weeks and it's open to everyone anywhere in the world. So if you would like to join us for that, yeah, keep your eyes and ears peeled for that information that's going to be coming out soon. Also, the NKS book club is happening every week at this point, still on Sundays. So please join the Discord channel to join in for that. We're busy looking at every chapter. I think we're on chapter 5 at the moment of New Kind of Science. And yeah, we're going through all the examples. And if there's anyone out there that would like to help contribute in terms of the actual code for NKS, we're currently running a little initiative at the Institute to do full code coverage on the entire NKS book. So if you'd like to practice writing Wolfram language and really computationally understanding the ideas from that book, yeah, please join the Discord and engage with us there. Otherwise, yeah, thanks so much for this. And are we doing any more live streams this week, Dugan, or are we going to see one next week again?
not this week, but next week.
Next week. Great. Okay. Enjoy your weekend and the rest of the week, guys. Bye.
Thanks, Enjoy the weekend.
Bye for now.